In this video, we look at quadric surfaces that have equations with one variable raised to the first power and the other two variables squared. There are two types. We're going to look at both of those types, and then we'll look at transformations of these functions. So here is the first type. Let's say your equation looks like this. You have z minus a constant equals x minus a constant squared over a squared plus y minus a constant squared over b squared. This is called an elliptic paraboloid. And we'll see why that is when we look at the traces in the xy plane, the yz plane, and the xz plane. Just like the last video, we're going to look at quadric surfaces that have centers that are centered at the origin, just to make these as simple as possible before we get into transformations. So here's an example. Let's say we have z equals x squared over 4 plus y squared over 9. Notice that it has that form up there. Notice the z is raised to the first power, and x and y are both squared. And notice that we're adding both of these. So just to figure out what this looks like, let's look at the traces in the xy plane, the yz plane, and the xz plane. In the xy plane, that's where z equals 0. We'll have the following. If z is 0, we have 0 equals x squared over 4 plus y squared over 9. Now remember, this is a number that is always positive except for when it's 0, and this is a number that's always positive except for when it's 0. Any squared number is going to be positive or possibly 0. So the only way that we can get a 0 out of this is if this is 0 and this is 0, and this is 0 and this is 0 only at a single point. The rest of the time it's positive. So that means xy must be 0, 0. The entire trace in the xy plane, here's x, there's y, is just a single point. It's just 0. When x and y are 0, z is 0. Okay, so that's one of our traces. Or, excuse me, that's just one of our, points of intersection in the xy plane. Now let's look at what happens when y equals 0. So we're in the xz plane. Well, if y equals 0, we get z equals x squared over 4 plus 0 squared over 9. So we just get that equation right there. I hope you recognize that as a parabola. Now, we can draw this in the xz plane. I could draw my x-axis over here. That's what we're used to. But notice it's a right-handed coordinate system. If my z-axis is going straight up, my x-axis is coming like right out at me from the perspective that I'm looking at this from. So with that in mind, rather than putting the x-axis over here, I'm going to put the x-axis over here. So I've got z going up, x going out, and then if I rotate it, rotate it 90 degrees, then I would see this picture right here. So I'm going to have x equals, or the positive x-axis on this side. Now because of symmetry, it doesn't matter in this case. I hope you guys recognize that as a parabola. When x equals 0, z equals 0, 0 squared over 4. And when x equals 2, or negative 2, we get 2 squared over 4, so 4 over 4, which is 1. Or when x equals negative 2, we get negative 2 times negative 2, which is positive 4. 4 over 4 is 1. So that's what we're looking at. We've got a parabola, and it's sort of stretched horizontally, or you can think of it as shrunk vertically by a factor of 1/4. So when x is negative 4 or 4, we're going to have 4 squared over 4, which is 4. And negative 4 squared is positive 16, because negative times negative is a positive. 16 over 4 is 4. And so this is what our trace looks like in the xz plane. So we've got this plane over here. It's a little bit hard to draw. It's like going behind the y-axis there. There's the xz plane. And in the xz plane, our curve looks like this. Something like that. Okay, now let's see what it looks like in the yz plane. In the yz plane, that's in the back, that's where x equals 0. So this is gone, and we just have z equals y squared over 9. That's exactly the same thing. It's another parabola. It's just in the yz plane. And instead of being shrunk vertically by multiplying all the z values by 1/4, we're multiplying all the z values by 1/9. So it's 1/9 as tall as it would have been if it was z equals y squared. So when y equals 3 or negative 3, z equals 1. And so that's what our trace looks like. Now over here, we're talking about the yz plane. That's perpendicular to the xz plane. Picture's getting hard to see. But in the yz plane, we have another parabola, so it looks like this. And when you put all those pieces together, you get a shape that looks like that. So that's called an elliptic paraboloid. And you might say, where are the ellipses? We see some cross sections are obviously parabolas. In the xz plane, wherever y is equal to 0, and actually whenever y is a constant. If we keep taking different slices of this, we're going to have a parabola whenever y is a constant. Whenever x is a constant, we'll get parabolas. When z is 0, we get a single point. Let's say that z is not 0. Let's say that z is something else. Let's say that z equals c squared. And you'll see why I squared it in just a minute. And then I have c squared equals x squared over 4 plus y squared over 9. Actually, I don't even need it to be squared. Let's just make it c. Then we'll divide both sides by c to get 1. Do you see that that's going to be an ellipse? So this is an ellipse. Well, I guess we could square it. I'm going to put that back. So in the denominator, 4c squared is the same as 2c, quantity squared. 9c squared is the same as 3c, quantity squared. So we're going to go plus and minus 2c units in the x direction. Yeah, I'll put x over here and y over here. I'm just going to use c equals 1 for right now. Plus or minus 3c units in the y direction. It's going to be minus 2c and positive 2c. This is going to be positive 3c and negative 3c. And that's what it's going to look like up here in the plane where z equals c squared. So if c equals 2, we're going to be on the plane where z equals 4. And y is going to go from negative 6 to 6, and x is going to go from negative 4 to 4 because c equals 2. If c equals 1, y goes from negative 3 to 3, and x goes from negative 2 to 2. So as c takes on different values, as c gets larger and larger, which means that z is also getting larger and larger, our ellipse gets larger and larger. But this proportion, this 3c, this 6c long axis to this 4c long axis, like that proportion stays exactly the same. It keeps increasing as z increases. And that's actually what you see over here. When z equals 1, we get an ellipse that's kind of small. When z equals something larger, we get an ellipse that's kind of larger. And as we increase, we get larger and larger ellipses. So you can see why it's called an elliptic paraboloid. We've got parabolas for cross sections parallel to the x equals 0 and y equals 0, and ellipses for cross sections or traces whenever z is equal to a constant. So this is an elliptic paraboloid. And let's look at the equation again. This is our particular example of an elliptic paraboloid. Notice I have z equals x squared over 4, so it's concave up in the x direction. It goes up. Now if this is gone, I have z equals y squared over 9, so it's also concave up in the y direction. So it's concave up in the x direction and the y direction. Looks like a parabola in both directions. And then you put those two pieces together and you get this elliptic paraboloid. Notice that x and y are both squared and they have the same sign. This is positive and that's positive, and we have z over here. So that's an elliptic paraboloid. We're going to come back to that in a little bit. The next type of surface is called a hyperbolic paraboloid. Oops, HY, hyperbolic. And our standard form for that is this. So it might look like this, or this has got a squared y term, a squared x term. This term's positive, that one's negative, and z is raised to the first. Or we could flip these. This is one that is very hard for me to draw. I'll just call that a squared now. But let's think about what it looks like, and then we'll try to put the pieces together to get a sense of what's going on. There's also lots of real-world examples that go with this one, so we might be able to visualize it even if we can't draw it. So here is our simple example. Let's make it very simple. Let's let a and b equal 1. Center it at the origin. So I have y squared over 1 minus x squared. So this is a hyperbolic paraboloid. If we let z equal 0, we'll see the trace in the xy plane. So we have 0 equals y squared minus x squared. Any ideas what's going to happen there? Well, we could solve for y. X squared equals y squared. And if I'm trying to get y by itself, I'll take the square root of both sides. Don't forget the plus or minus. So we have y equals plus or minus square root of x squared, so that's x. So the trace in the xy plane is just y equals x, so that's a line. And y equals negative x, that's another line. Okay, these are not to scale. I didn't do a very good job of drawing my pictures, but that's okay. All right. I'd say, okay, there's no hyperbolas or parabolas yet, so I'm not really sure why this is a hyperbolic paraboloid, but we'll see. Okay, so we let z equals 0 and we got this. Now let's let x equals 0. Then we're in the yz plane. Well, if x is 0, that's gone, and we're just left with z equals y squared. And we all know what that looks like. If this is my z-axis and that's y, that's just a parabola facing up with its vertex at the origin. So it looks like that. You might say, how is that picture and that picture going to go together? We'll see. We'll see it in a little bit. And then finally, we let x equal 0, we let z equal 0, let's let y equal 0. Then we are in the xz plane. And so if we're in the xz plane, this one's gone, and we have z equals negative x squared. That's a parabola 2 with its vertex at the origin 2, but the negative flips it. It flips it upside down. Now again, because of our right-handed coordinate system, I'm going to put the x-axis over here and the z-axis here, so I can imagine taking this and turning it whenever I look at it in 3D. Z equals negative x squared, just a parabola facing down. You might say, how on earth is it a parabola facing up in one direction and a parabola facing down in another direction? Have you ever heard of a saddle or a saddle point? That's what this looks like. Now, before we go to the saddle picture, and we talk about that in more detail, I want to focus on this picture here. When z equals 0, we get these two lines with opposite slope. Let's say z equals a different constant. Let's say z equals 1. Just to get a better sense of what's going on. When z equals 1, we have 1 equals y squared minus x squared. That's not a set of lines, that's a hyperbola. There's an implied 1 squared there and an implied 1 squared there. So we go plus and minus 1 unit from the origin in all 4 directions. Make a little box. Draw these axes. Notice that those have the equations y equals x and y equals negative x. And because the y is positive, it opens in the positive y direction. You might say, what does that mean? I still don't know. Well, this is what it looks like when z equals 0. And this is what the cross-section looks like when z equals 1. Let's think about what the cross-section looks like when z equals 2. Let's put it on the same plane over here. Well, to make it look like a hyperbola in standard form, let's divide both sides by 2. Everything gets divided by 2. Now I've got y squared over square root of 2 squared minus x squared over square root of 2 squared. I'm only doing that because I want to know how many units to go in every direction, and it looks like I'm going to have to go square root of 2 units in both the x direction and the y direction because it's under the x and it's under the y. That's square root of 2 squared. Numerical approximation for square root of 2 is 1.4 approximately. So we're going to go, this is negative 2, that's positive 2, here's positive 2 and negative 2, and we want to go out 1.4 units in all of those directions. So make a box out to 1.4. Notice it has the same asymptotes, so those are the same. But now, and it still opens in the y direction, but now it looks like that instead. Not supposed to cross, but it gets very close to that. So z equals 0 is down here. And when z equals 1, if we go up 1 level, we're on these red curves. And if z equals 2, we go up 1 level, we're on these blue curves. Let's say, what on earth does that mean? Well, let's put all these pieces together now. See what's going on. This is concave up in the y direction and concave down in the x direction. So excuse my picture, I'm going to do the best I can. I always bring Pringles to work on this day in class. When I remember, I do. Okay, so if it's concave up in the y direction, it's going to look roughly like this in the y direction. And it's concave down in the x direction. hard to draw. You see it? It's like a saddle. It's going down in the x direction. So if we look at it from this angle, it's sloping down, but in this angle, it's sloping up. And if we take slices with the z-axis, or parallel, not parallel to the z-axis, parallel to the xy plane, z equals 0, all those slices are going to look like this. In the xy plane, we just get these lines. At z equals 1, we get a hyperbola, and at z equals 2, we get a different hyperbola, because that's where those planes would intersect this saddle. So this was z equals y squared minus x squared. Any ideas on how it would change if it was x squared minus y squared? Notice z is raised to the first power. Now it's going to be concave down in the y direction and concave up in the x direction. Ooh, how am I going to draw this? I'm going to try. That's what I'm going to do. I'm just going to try my best. So it's concave down in the y direction and concave up in the x direction. Sorry guys, these aren't great pictures, but I hope you get the idea. This is the xy plane back here, and it's going concave up that way. And then it's concave down in the y direction, so it looks like this on this side. So that's our saddle. It's just been rotated 90 degrees. Concave up, concave down, or concave up and concave down. Alright, so those are what are technically called hyperbolic paraboloids. Sometimes people will call them saddle points. I also like to just think about Pringles. I'm not like a huge Pringles fan or anything. But if you've ever had one of those potato chips, you've seen a hyperbolic paraboloid before. If you actually have ever ridden horses, if you've had that privilege, if you've ever seen a saddle, it looks like this. Otherwise, it would be very uncomfortable, wouldn't it? So saddles look like this. That's why it's called a saddle point. Pringles look like this. They're really hard to draw. In our class, I'll never ask you to draw one of these because they're so hard to draw. But I might ask you to match an equation to a graph of one of these. Notice it's concave up in x direction, concave down, or excuse me, concave up in the y direction, concave down in the x direction here. But that's in the z-axis. It's like everything is emanating from this z-axis. That's the variable that's raised to the first power. So even though I've got z equals y squared minus x squared and z equals x squared minus y squared, it could just as easily be y equals x squared minus z squared or z squared minus x squared. The y could be raised to the first instead of the z. The x could be raised to the first instead of the z. And those would be hyperbolic paraboloids too. And they would be oriented a little differently in three-dimensional space. Okay, so we've got our two new quadric surfaces. Hyperbolic paraboloids that look like this, and elliptic paraboloids that look like this. Now notice the similarities and the differences between these two. The equations are basically the same. The only difference between them right now as they stand is for the elliptic paraboloid, which has this shape. The x and y terms, they're both squared, z's raised to the first, but notice that they're both positive. Now over here, one's positive and the other one's negative, and z is raised to the first. So we've got those saddle points that look like that and the elliptic paraboloids that look like this. Now, if they both happen to be negative, well, that is an elliptic paraboloid, but we've just changed it a little bit. We've changed it the same way that we change graphs of functions in college algebra. Whenever we talk about transformations of y equals x squared, we shift left, we shift right, we shift up, we shift down, we reflect across the x-axis, we stretch it vertically or horizontally, we shrink it vertically or horizontally. All of those things can be done to these. Instead of y though, instead of thinking of y as the dependent variable, the thing that changes when x changes, we're thinking of z as our dependent variable now. So if these were both negative, let's see what that would do to the graph. This is just an extension of what you did back in college algebra or pre-calculus or maybe in high school algebra. So back in high school algebra, or the algebra class where you learned about transformations, we learned that if I have y equals x squared and I add 5 to it, that just takes the graph of y equals x squared, which is down here, and it adds 5 to all of the old y values. So it takes these y values and it adds 5 to them. So when y was 0 before, now y is 5. And when y was 1 before, now y is 6. And so on. So every single point gets lifted up 5 units. This one becomes this one becomes this one becomes this one. And we keep going. And we get y equals x squared plus 5. The entire graph shifts up 5 units. Or, you remember this, that's going to shift y equals x squared. Is it to the left or to the right? Well, the vertex is going to occur, it's going to happen whenever x is equal to, or whenever this expression that's being squared is equal to 0. So the vertex occurs at x equals 2, because x minus 2 is 0 when x is 2. So what does that mean? It means if you're subtracting 2, you're going to shift to the right. Not the left, but the right. Because that's the x value that would make that 0. And we're basically shifting that 0 point over 2 units. So this shifts our graph to the right 2 units. This one shifts it up 2 units. Remember this guy? I took all my y values from before, which were positive or possibly 0, and I multiplied them by -1. Opposite of 0 is 0, but the opposite of positive 1 is -1, and the opposite of 4 is -4. And so we get exactly the same parabola, but this time it's been flipped upside down. We say it's reflected across the x-axis to be more technical, but I just think of it as flipping it upside down. So I flipped this upside down, I've shifted this to the right 2 units, I've moved this up 5 units. We can also, of course, move left and we can go down. So let's say we want to go left. Let's say we have y equals x plus 3 squared. That just means this will equal 0 when x equals -3. And we get a graph that looks like that. And if I have y equals x squared minus 2, we just take the whole graph and shift it down 2. So this is just a quick review of some of our transformations. Now, we're going to go to 3D. You might ask yourself, what does this look like? You might say, okay, I don't have any surfaces on my list of quadric surfaces, my cylinder, my plane, my sphere, all those things that we've just learned about. I don't have any surface that looks like this, and you'd be absolutely right. But notice that the x and the y are both squared, and then they're both negative, and z is raised to the first power. So what this is it's an elliptic paraboloid, but we've done some transformations to it. Let me factor out that -1. Do you see the elliptic paraboloid now? If we have z equals x squared plus y squared, that's an elliptic paraboloid. Actually, I guess it's a circular paraboloid, right? When z equals a constant, we get a bunch of circles. So let me start with that. Z equals x squared plus y squared looks like this. It's concave up in the x direction, concave up in the y direction. Together we get this. Multiplying that quantity x squared plus y squared by -1 flips it upside down, just like multiplying the x squared by -1 flipped that upside down. And what does that 5 do? It does the same thing as that 5. It shifts it up 5 units. So this graph actually looks like this graph. So you're going to go up 5 and like this. It's the same shape, we just flipped it and we shifted it up 5. So if you've got two variables, they're both squared, but they have the same sign. If this is negative and that's negative, it's an elliptic paraboloid. If they're both positive, it's an elliptic paraboloid facing up. If they're both negative, it's been flipped. It's an elliptic paraboloid facing down. Now all of that changes if that z is squared. If that z is squared, it's not an elliptic paraboloid at all. It's one of the other quadric surfaces that we talked about. Okay. And let's look at one that's not centered at the origin. Let's say you've got z equals x minus 1 squared over 4 plus y plus 2 squared over 9. Well, notice the x and the y are both squared. Z is raised to the first, so we have an elliptic paraboloid. But when I'm looking for my center, it has coordinates x naught, y naught, z naught. The x naught, y naught, and z naught come from what we're subtracting from the x, the y, and the z. Now, you might have like a -5 over here. You could also move that +5 to the other side. That would be fine as well. But the center for the x naught and the y naught is really easy to see. X naught is 1. You take the opposite sign from what's there. Y naught is -2. You also take the opposite sign from what's there. And since we're not subtracting anything from the z, and there's no constant on this side, z naught is 0. So this is just an elliptic paraboloid that's been shifted a little bit. Subtracting 1 from the x, it does exactly what subtracting 2 from the x did up here. Remember, we took our parabola and we shifted it 2 units to the right. If I subtract 1 from the x, that's going to move us 1 unit in the x direction. It's not right this time, it's going to be forward. So we're going to go 1 unit in the x direction. And adding 2 to the y's, remember that shifted this graph to the left when we added 3 to the x's? Well, adding 2 to the y's shifts everything actually to the left 2. We go 2 units in the negative y direction. So there is our vertex. It's x equals 1, y equals -2, z equals 0. And we look at this, and it's elliptic paraboloid. The numbers under the x and the y tell you which direction is going to be larger. Since the larger number is under the y squared, it's going to be longer in the y direction than it is in the x direction. If I look at those cross sections that are ellipses parallel to the xy plane, the ellipses are going to be horizontal. It's going to look like this. So I'm just going to draw a paraboloid that looks roughly like that to me. Okay, and of course this continues up forever. We can only draw part of it. So that's this graph. Now of course we could switch. We could say, let's say y equals z squared plus x squared. Well, now, instead of opening around the z-axis, just notice that the elliptic paraboloids opened around the z-axis when z was raised to the first power. This one's going to open around the positive y-axis. So it's going to look like that. And then let's think about how this would change if we said x squared plus z squared and we subtracted 5 from it. You see that we're taking all the old y values and we're subtracting 5 from those y values. So this is y equals x squared plus z squared. And then this one just as its vertex at -5, but it also opens in the y direction. This one is y equals x squared plus z squared minus 5. Okay, so keep those transformations in mind as you're graphing your functions. In the next video, we're going to talk about the types of problems that you could see on your quiz. So what I might do is give you graphs of a function and give you graphs of surfaces and equations of surfaces, and then ask you to match the graphs to the equations. Or I could just give you the equations and ask you to sketch them. Now, your sketches don't have to be perfect. Just any kind of description will help. If the graph gets really bad, just start trying to describe the surface in words. But do the best you can. I mean, you've seen my graphs are not great, but hopefully they're good enough to give you some sense of what's going on. And so we'll do that in the next video.